Hello everyone, this is Morthekai. In this module we would like to talk about luminescent dating technique, both principles and applications. Actually we are distributed in such a way that principles I will talk and then application part Dr. Nawaj Ali will talk. In the principles module, I would like to talk about what is the signal we are talking about, and then how the signal is acquired in the system, and then how we measure it, and then how we synthesize and present as a date. So in short, this part is like a quantification of the word paleo. Also in this principle I would like to talk about how we collect the samples. This is a metal pipe. Actually this is already collected samples are there. We make a trench and then we insert the pipe hammer inside the sediment, and then we collect the samples outside, and then we close the pipe before it is exposed to sunlight. So in that sense, once we collect the sample, this is unexposed to sunlight, and then we brought to the lab, we open the pipe, we retrieve the sample that is unexposed to the sunlight, and then we open in the lab, which is subdued light, so that there is no exposure to the light, and then we prepare the samples. So this is the way we prepare we collect the samples and we prepare in the laboratory. So I would like to talk about analog to this dating technique. It's a Singvis beaker example, let's call. In principle, this luminescent dating technique is like there's a beaker that is being filled with water, and then if we know the total amount of water in drops and then the dripping rate, then we'll come to know what's the time lapse since the beaker has been kept under the tape. So total volume divided by the drip rate will give the age of the beaker that has been kept under the tape. So what is the signal we are talking about? Compared to the analog, water is the signal in the beaker. Similarly, trapped electrons are the signal that is stored in the crystals. For example, we are talking about let's say quartz, that is silicon dioxide, but no perfect crystal in the world. So the silica that is replaced by aluminum, aluminum can be replaced by potassium, sodium, lead, etc. These are the impurities. Similarly, there are defects also. There are ions that are missing in the lattices. So there are both the defects and impurities trap the electron that is coming nearby that way. So there are traps which can trap electron. There are traps that can trap holes. So these stored trapped electrons and holes are the signals for our dating technique. So how do we measure that? How the signal that is acquired in the crystal? There are ambient radioactivity in the sediments that emit alpha, beta, gamma, muon. They are ionizing radiations. For example, uranium-235 that emits 7 alphas, 4 betas and gamma. Like that, uranium-238, thorium-232 and potassium-40. They are long-lived radioactive nuclides. So they all the time emit alpha, beta, gamma. These ionizing radiations knocked out electrons from the sediments or the quartz crystals. These electrons, when that happen to go near with the trap, they are trapped. So this is the way that signal that is acquired constantly into the system that's called quartz. Let's say quartz. We can also talk about feldspar and other minerals. Now one more point is the acquirement rate that should be constant. And then there's a small problem. Actually, water content in the sediment will control the constant dose rate. For example, water absorbs radiation. So when the water is coming into the system, that lessen the dose rate. Similarly, if suppose the movement of radioactive nuclides, let's say uranium, thorium, potassium, if they are moving out or coming into the system, then also the dose rate that changes. That's not constant. That we have to consider when we finalize the age estimates. So here I would like to talk about how do we measure this signal. As I already mentioned, the signal is trapped electron. We cannot measure or we cannot see an electron. So now we have to use an indirect measurement. So what we do, this slide shows a trapping of electrons. How the trapping happens? In this valence band and conduction band, maybe you would have known that metal, there is no gap between valence band and conduction band. Semiconductor has small band gap. We are talking about insulators, that's wide band gap insulators. So there is a forbidden gap of 7.7 or 8 eV between a valence band and conduction band. So because of the impurities and defects which we talked about earlier, traps are there. That means the electrons can be trapped. For example, if suppose no traps, no defects are there, when the electron goes from valence band to the conduction band, upon the exposure to the ionizing radiation such as alpha, beta, gamma, these electrons move around in the conduction band freely, and then when that encounter a trap, either that is hole trap or electron trap, that electron or hole will be trapped in the trapping centers. So this is the trapping. Now, as it is trapped in the traps, unless you give energy, that electron will not come out from the trap. Now, this is our signal that is stored for from seconds to billion years. We are interested in the electrons that are trapped in the traps for billion years. Also, during ionizing radiation to the crystal, alpha, beta, gamma, once the electron is being trapped in the traps, that also emit luminescence. That we call RL, radioluminescence. That also one can use for dating. That is in details. Now, how we read out or how we measure the trapped electrons? Now we give energy either in a heat or a light. So this thermal energy or optical energy will detrap the electron from the trap that goes to conduction band. Upon coming back to the valence band, it may encounter a recombination center. Recombination center is nothing but a hole center. That's the absence of electron, that is in need of electron. Once it comes by that way, it attract and recombine. Upon recombination, luminescence will come out. That luminescence correspond to the concentration of trapped electrons. Similarly, for example, one photon comes out, that means that one photon may correspond to the one trapped electron in a trap. So that's the way we read out the luminescence signals. So it's an indirect measurement. We can't measure the trapped electrons. We measure the luminescence that is correspond to the trapped electrons. So as I mentioned, we can give heat to detrap the electron. That we call thermoluminescence, thermally stimulated luminescence. We are stimulating the electron to come out from the trap, end up with luminescence, that we call thermoluminescence. If we use light, then we call optically stimulated luminescence. In this, actually we combine all. The y-axis is light intensity, x-axis is time. For example, during ionizing radiation, either by beta or X-ray or alpha particles, so we give, it is exposed to the ionizing radiation. During ionizing radiation exposure, luminescence that comes out, that we call radioluminescence. Once it is trapped, phosphorescence start coming out. We are not interested in the phosphorescence or fluorescence that is emitted in seconds lifetime. We are interested in the phosphorescence that is being emitted at billion years or million years lifetime. Now once that material is buried or not exposed to the sunlight, we collect the sample, we bring to the lab in light tight manner. We prepare the specific minerals, let's say quartz or feldspar. We use light as a stimulation source. The optically stimulated luminescence that comes out, that we call OSL. That is when we use light as a stimulating source. Now if we use heat as a stimulating source, then what it comes as thermoluminescence. The peak OSL decays with time. TL give you a glow curve picture with a peak. The peak corresponds to the position of a trap in the crystal. So this slide shows dose measurements, the instrumental part. As we detect the luminescence, that's the photons, so we need photomultiplier tube. We keep the sample in the sample plate, and then beneath that there's a heating element. So if we heat, TL will be detected in the PMT, thermoluminescence glow curve, and we can also use laser diodes or LEDs for optical stimulation. And then right hand side there's a beta source, that is a calibrated beta source that gives a known, that emit known dose irradiation to the sample, so that we can calibrate the luminescence photons with the dose that received. Dose is nothing but the energy received per milligram of sample of quartz or feldspar. This slide shows there are the available instruments in the commercial market. Left hand side there's a RISO reader from Denmark that's widely used, and also USA they make, Daybreak company makes. Below that's Freiberg system from Germany. So these are the available readers. What we have in our laboratory, that is RISO made. There are also attempts to make indigenous TL OSL reader by Bark. That's also going on. Very soon they will be successful. Main thing in this system is the stability. As I mentioned, luminescence light will come out at all the time, ranging from nanoseconds to billion years. But we are not interested in the short time emission. We are interested in the electrons that can be stored in the system for billion years. There's a equation as shown in the slide. There's a probability for detrapping. That's a function of trap depth, that is E, and S is the frequency factor, is nothing but attempt to escape electron. Also the ambient temperature, that is T. More the trap depth, stability is more. Lesser the ambient temperature, stability is more. Lesser the S, that's the frequency factor, stability is more. Here, right hand side, there's a TL glow curve starting from room temperature to 450. There are 4 prominent peaks in the TL glow curve. 110 degree, that's for quartz, and 325 degree TL peak, that's for the quartz. As 110 degrees is less stable, we don't use that, and then 320 degree Celsius TL peak, that's a dosimetry peak. That means that is the peak that will be stable for billion years. So we remove the unstable part by preheat method, isolate the high stable signal, we give light. Once we give light, the OSL comes out, that's the exponential decay curve that has fast component, medium component, slow component. We are interested in fast component, that nothing but once you give light, the signal that comes first. That's what we use for dating purpose. Age equation, you can see luminescence divided by luminescence acquirement rate. You can see the equation. We are interested in low LET, that is linear energy transfer. Beta, gamma and cosmic ray, we can classify into low LET. Alpha is different from other beta, gamma and cosmic ray in terms of linear energy transfer. That is nothing but if the gamma penetrates the crystal, it gives lot of trapped electrons, but the traps are little. So efficiency in terms of alpha is less. But that is same for beta and gamma. So if you rearrange the equation, second equation, luminescence can be also equated with dose. As I mentioned already, dose is energy that is absorbed per milligram of sample. Final equation shows that is we remove the alpha dose layer of quartz or feldspar by removing the layer, by etching the sample with hydrofluoric acid. Also, not only uranium, thorium, potassium from the sedimentary context, also we get dose rate from cosmic ray. Cosmic ray dose rate is a function of latitude, altitude and overburden, and that is typically of 0.2 gray per 1000 years. another important parameter is dose rate. That is how, at what rate the luminescent signal or the dose is being acquired by the crystal. We use gamma spectrometry. We can also use XRF, ICP-MS and other techniques to detect the uranium, thorium, potassium. Here this slide shows gamma spectrometry based on sodium iodide crystal. So we have a specific gamma energy for potassium, uranium and thorium. So by comparing the standards and sample, we estimate uranium, thorium, potassium from the surrounding sediment. Once we calculate the uranium, thorium, potassium, then we can convert all these in terms of dose rate, in terms of beta and gamma. So we can measure dose and dose rate. So age equal to dose by dose rate, that will give the age. Next slide will show how we measure the dose. For that, dosimeter is needed, dosimetry we call. We measure the natural sample, luminescent from that. As I mentioned, OSL is a decay curve. The area under the curve will give the total luminescence that has been resulted from the natural irradiation during the burial. So once we measure, in the x-axis, laboratory dose, that is dose that is given in the laboratory, y-axis, that's OSL signal. Then we give known laboratory dose to the crystal and construct the dose response curve. Then we interpolate the natural luminescence into the growth curve to get the laboratory dose that is equivalent to the natural dose. So this is the way we measure the absorbed dose. There are checkpoints. We measure recycling ratio. That means we give the laboratory dose twice or thrice and whether it is reproducible or not. Similarly, recuperation is nothing but we give nothing and try to see whether that gives nothing or not. We do dose recovery test where we give a known laboratory dose and try to retrieve using the protocol we use. So if that is recovered, then we are confident about the protocol. So this is the way we measure absorbed dose. Finally, what is it we date? Luminescent dating technique, if you measure luminescence or we follow the procedure on any sediment, it will give some number, but what it corresponds to. So the number corresponds to the last resetting event. When the sediment has been exposed to sun or when it has been exposed to the heat. So that is the event we are dating. For example, archaeology, potteries are there. We heat and then pottery is abandoned, that is buried in the sediment context. We retrieve them, measure the number that corresponds to, that's when the pottery was exposed to heat more than 400 degrees Celsius. Finally, statistically, we measure many samples, many aliquots, many subsamples we measure. During transportation, some grains would have been well reset. That depends on the agent by which it is being transported. If it is wind transport or water transport, some grains would have been well bleached or well reset, some are not. That also we can isolate by using these statistical methods to isolate the well bleached dosed population for the age estimation. I would like to stop here now. For the applications, Dr. Nawaj Ali will talk.
Hello everyone, my name is Sheikh Nawaj Ali and I am a scientist at Birbal Sahni Institute of Paleosciences, Lucknow. So I am going to take from where Morthekai has left. I will be talking about the application of OSL chronology in different environments. So I will be talking about three main different systems. One will be the glacial system, second one will be the fluvial system, and third one will be the geoarchaeology, that is the application of OSL ages in archaeology. So as Morthekai has said that we are using quartz and feldspar for dating. So these minerals are almost present everywhere. So this makes the sampling for OSL dating very simple. If we take an example of a glacier and try to establish the chronology of a glacier, what we see that when there are conditions that are feasible for any glacier to advance, the glacier advances. The feasible conditions are that it is having a good precipitation and the temperature is cold. So if the conditions are better for glacier, it will advance, while if the conditions are towards the warmer side, the glacier will start retreating. But when this glacier advances, it leaves behind the moraines, and these moraines are the traces which will help in establishing the extent of glacier in the past. The moraines and fields look like this. This is a literal moraine which is present in the central Himalayas. So if we have to reconstruct the glacial boundary in this region, we will see that this area was covered with the glacier for a long time of period, but we don't know exactly the age when the glacier was extending to this stage. So what we do, we go to the field, we try to look for suitable samples. Suitable samples means those samples which would have been exposed to sunlight for enough period that the signal is bleached. As we know, moraines are composed of unstratified and unsorted sediments, so we have to look for those sediments which have got enough exposure in the sunlight so the signal is bleached. We see in the photograph that there is a sand lens present within the moraine, so we collect samples from these sand lenses and we take them to the laboratory. So after getting these samples dated, as Morthekai has said in the last presentation, we get ages of different moraines. So we establish the chronology of glacial events. Based on these events, what we get? So if we see, we have generated various glacial extents and we have dated these time periods when the glacier was at that particular point. After having that, we estimate the temperature at which that glacier might have achieved that position. So in a way, it gives us the past temperature. If a glacier has expanded tens of kilometers downstream the present day glacier snout during LGM, and we have calculated that during LGM the temperature decline was around minus 2.2 degrees Celsius. Similarly, when we say fluvial systems, we often have seen floods like the flood of Uttarakhand in 2013. These floods generate lots of sediments and these sediments are deposited downstream areas. So the photograph shows a river terrace which is an example of aggradation. That means the river has deposited sediments in the past to this height and the buildings have been constructed on this river terrace. But this is an example that river has been flowing through this channel. So if we are constructing buildings on these river terraces, they are prone to destruction in future floods. Now, when we are talking about floods, can we date the floods or can we see the cyclicity of floods? For that, we have to go in the past. Again, we have to look for sediments within these terraces, and these terraces will give us an age of the event when they were formed. So if we have multiple events of these aggradational events, we can have a cyclicity or we can have a time frame when the floods have happened and when they can occur in the future. In this, I am going to show another example of a terrace. You can see this is a 35-meter section and the bottom 30 meters are totally of sand. But on the top of this section lies a boulder bed, which is an example of flood deposit. So the river was flowing at this height and this has been deposited by the flood. So we cannot say that the locations that we use for construction in the hilly areas, that is mostly the terraces, those are safe for construction, or we should do some engineering work before we construct in these places. Another example is the geoarchaeology. Can we use OSL ages in establishing a relationship between human settlements and the time period? So we have seen that a lot of geoarchaeological sites have potteries, but if we see in most of the sites which are located in higher Himalayas or the foothills, we don't find any pottery in them. So when we don't have any pottery that is a datable material, we can go directly to the rock tools. Now OSL has been using the exposure OSL ages, which can directly date the rocks that have been formed by the early humans. So this will give us a climate-human interaction system and it will help in understanding the migration patterns through the Himalayas in the past. take home message will be that luminescence dating is an absolute dating method. Sediments from few years to thousands of years up to lakhs of years can be dated, and the age that we get on the sample is the age of resetting. That means that when the sample was exposed to sunlight or heat will be dated. Thank you. Hope you have enjoyed it, and we move on to next lecture.